Started recording.
Okay, so welcome back to lecture 17 on Riemannian symmetric space. I want to just clarify one doubt which was really asked to me by Tapendu. So this is the proposition: let S be a submanifold of Rn, and let F from S to S be a smooth map, so that F extends to a linear map F tilde from Rn to Rn, so that for any P belongs to M, this dFP is equal to F. Okay. Look at this. Look at this statement very carefully. See, this F is a map from S to S. Okay.
Oh, what is M here?
What M?
You said P for P belongs to M. It should be M or S?
S, S. Yeah. Okay. P will, F belongs to S. It will be, sorry. Okay. F is a map from S to S, and F extends to F tilde. Okay. So dFP is equal to F. This statement doesn't really make sense actually. Okay. But actually, because F is a map from S to S, and if V belongs to TPS, F of V is not may not be well defined. Actually, this should be actually, but whereas F tilde, this is a globally defined map from Rn to Rn. So this should be actually, if you want to write this, this should be really F tilde restricted to TPS. Okay. So this should be like that. So I have to actually do this thing because I did a mistake here. It killed the TPS because usually what one does actually, sometimes people write the extension map F tilde as F also. So that is the reason I did wrong little. So let us correct the proof little bit. Let F be V belongs to TPS. Then there exists a curve gamma with gamma 0 is equal to P and gamma prime 0 is equal to V. Then dFPV is equal to d by dt, t is equal to 0, f of gamma t, and here f of gamma t is simply write f tilde gamma t because f is equal to f tilde. So, okay, now so that is really, so this will be so since f tilde is linear, this is equal to f tilde b as f tilde is linear. So Tapendu, is it clear now? Hello, Tapendu, are you there? Hello, Pritam, are you there?
Yes, brother.
Oh, I see. Okay. Actually, HRI connection is very down today. So, okay. So I have told you that isometries are rigid in a certain sense. So this is the thing. Let M be a Riemannian manifold, and let P belongs to M. Let phi comma psi belongs to In. This so that phi P is equal to psi P, and if phi P is equal to d psi P, then phi is equal to psi. That means isometries are completely determined by its value and derivative at a given point. That I will really refer to as rigidity of rigidity theorem. That we call that isometries are rigid. Okay, so now recall we have defined this so-called real hyperbolic space, this Hn. Okay, real hyperbolic space. So what is the definition? Let x belongs to Rn plus 1 and y belongs to Rn plus 1. I defined this bilinear product xy. This x1 y1 plus x2 y2 plus xn yn minus xn plus 1 yn plus 1. So this Hn is the thing that the x belongs to Rn plus 1. So that x is really minus 1. Xn plus 1 is greater than 0. So this was the definition. We have seen that we saw that Hn is a smooth connector, smooth and embedded submanifold of Rn plus 1 with dimension n. You have seen that. And also we have seen that this SO not n comma 1 mod SON, this is homeomorphic to this your HN, and this is homeomorphism, and it is much more than homeomorphism. This is actually diffeomorphism. Okay, so now I take this the differential form d1 square plus du2 square plus not differential form, sorry, it is the 0 to tensor. So du n plus 1 square. Okay, this is a 0 to tensor on Rn. I restrict that to Hn, and so this makes sense. And so G is a actually 0 to tensor on Hn. Okay. Now let U V belongs to your TPHN. By what is TPHN? TPHN is equal to P perp, where P perp is the orthogonal complement with respect to this is bilinear form. So with respect to this, and what is this by definition? This is really W belongs to Rn plus 1, so that WV is really equal to 0. Now, if you really what is GPUV? GPUV is really this bilinear product of UV, and I have shown that this bilinear product is really positive definite on P perp. Okay, so we have seen that this is really from P perp, and this is P perp is TPHN. TPHN to R is an inner product. So GP is an inner product on TPN. So GP is an inner product on TPN. That means G is a Riemannian metric on HN. So hence, so this implies G is a Riemannian metric on HN. Okay, and hence HN and G is a Riemannian manifold. Now what I am saying that let us take this thing. Let G is equal to, so let G is equal to really A belongs to UN1, so that A of Hn is equal to Hn, that which really preserves this Hn. And from this definition, it is easy to see that G is a group. G is a group. Now we have also seen that G is equal to really O plus plus N1 and disjoint union O minus plus N1. Okay. Now this is equal to same thing as A belongs to ON1, so that A En plus 1, this really belongs to Hn. You just check this thing. Okay, so after this actually I have discussed this thing. So G is equal to A belongs to N plus 1, so that A of Hn is equal to Hn, and G is equal to disjoint union of O plus plus N1, and O minus plus n1. Okay, so we will see that isometric group of this Hn is equal to G. Okay, we will show that. So, but what is isometric group of Hn? Isometric group of Hn, by definition, this is the all map from Hn to Hn, so that phi is a diffeomorphism. And this phi star G is equal to G. This is my thing. Now let A belongs to G. So since A by definition A preserves Hn to Hn, and matrix multiplication is a smooth function. So and this is an invertible map also. A Hn to Hn is a diffeomorphism. Okay, clearly, okay. So clearly, Hn is a diffeomorphism. Now I have to only show that phi star G is equal to G. Okay. So let U comma B belongs to TPHN. Okay. Now, so I will use that thing. See, A will extend to a linear map from Rn plus 1 to Rn plus n and n plus 1, and this is really A is a globally defined map. So as A is from Rn plus 1 to Rn plus 1 is linear. So DAP is really A. Okay. So now what will be, so G of AP, okay, DAP UV, DAP U, DAPV. So this is same thing as DAP U, DAPV, this binary product, and DAP is equal to your A, so AU, AB, but A by definition preserves this binary product, so this is UV, and this is really GP UV. Okay, so hence I get that GAP DAPU DAPV is equal to GPUV. This line actually means that A star G is equal to really G. If you are follow the definition, so that means so this implies A belongs to isometric of Hn, I of Hn. So I will get that A is any arbitrary element of G. Thus I get G is contained inside the isometry of Hn. Okay. Now I will prove the converse. So okay, so let let phi belongs to this let phi belongs to isometry of Hn. So let phi of En plus 1, this is equal to really P. This by definition this is belongs to Hn. Now d phi, I look at this En plus 1 from, so this is a mapping from Ten plus 1 Hn to TPHN. Okay. So okay, so this is let what is T in plus H1? So T in plus 1 Hn is really, if you follow the definition, really you can see that this is nothing but span of the vectors U1, E2, En. Now if you draw the picture here of this so-called hyperbolic space. This is my say hyperbolic space, and the tangent space at En plus 1 is this thing, and this is nothing but span of this so-called U1 to En. You can also do directly because you have explicit characterization of this T PHN. Okay, so let d pi En plus 1 Ei is equal to Ui, and Ui is belongs to TPHN by definition, and this is for 1 less than equal to I less than equal to N. Okay, now I take this Ui Uj. Okay, so okay, for 1 less than equal to I comma j less than equal to N. So I take this Ui Uj. So Ui Uj is really nothing but d. So g, this p. So Ui Uj, right? So but GP is really okay. So GP is really what G of A En plus 1, not A, this is phi. G of phi En plus 1, and Ui is equal to d phi En plus 1 Ei, and d phi En plus 1 Ej. So now I use this fact that G is an phi is an belongs to isometry of Hn. So that will give me G of En plus 1 Ei Ej. So here as phi belongs to IHN. So this implies that this is same thing as EI EJ, and this is called delta IJ. So what I am getting? So I am getting this thing UI UJ. This is called delta IJ. 1 I comma j less than equal to n. And since UI belongs to TPHN, so UIP this will be 0 for 1 less than equal to I less than equal to n, and PP is equal to minus 1 as P. So this implies, so okay, call this as star, these three equation of star. So from star, it is clear that if I take this matrix like A is really, this is like U1, U2, UN, and P. So this three condition of star will imply that this belongs to ON1, because this is the definition of ON1. Now as A En plus 1, this is equal to P, and this P belongs to Hn, and this implies A belongs to G, okay? Because G has an equivalent characterization is like this. Yeah, G is equal to A belongs to ON1, so that A En plus 1 belongs to Hn. So that means A belongs to G. So I have, okay, so A belongs to G. Okay, so and J is really contained inside some G. I have shown that G is contained inside IHN. So A is an isometry of Hn. Okay, now A En plus 1 is equal to P, and P is by definition phi of En plus 1. Okay, now A, okay, so dA En plus 1, okay, Ei, and this is dA is equal to A since A is linear. So this is AEI. AEI is really UI, and UI we have, this is the definition d phi En plus 1 Ei. So 1 less than equal to I less than equal to I. Okay. Okay. So now EIs are basis vectors of T in plus 1 HM. Hence we get A comma phi belongs to these both are belong to isometry of Hn, and A En plus 1 really is equal to phi En plus 1, and dA En plus 1 is equal to d phi at the point En plus 1. Okay. So these are both isometries. Now I can apply that rigidity theorem. So A and phi both are isometries. So this has same value at En plus 1 and same differential at En plus 1. Hence, by rigidity of isometries, A is equal to phi. Hence, by rigidity of isometry, A is equal to really phi. So this implies I get phi belongs to G. So I am getting where I started with element from IHN and I am getting this thing. So I get this IHN subset of G, and I have already proved that G is a subset of IHN. This is G is equal to IHN. So Manojda, is it clear?
Yeah.
Now Riju, is it clear, Riju? Riju.
Yeah, Munadar. Yes.
Okay, so exercise. So using actually rigidity of isometry, and a similar idea to that of HN, so that this I of Sn minus 1 is On, and I of Rn is really Mn. So I think that I think you should do this exercise. So last time I could have done this ISN minus On, but there was a disruption in the internet. So I think you should do it. Okay, so that you will be familiar to some concept. Now, so discussion. Okay, so first thing, let gamma from AB to M be a geodesic. I am assuming that here M is a Riemannian manifold. Okay, so now let T1, T2 belongs to this AB. So this is my picture. So this is my say gamma T1 and gamma T2. So now suppose this is my curve. The curve joining the portion of this gamma joining gamma T1 and gamma T2 is really say gamma T1 T2. So actually I have discussed this. Let gamma T1 T2 be the, so let us write be the curve joining gamma T1 and gamma T2. So let us draw the picture. Here gamma T1 and this is gamma T2. And this is my gamma T1 T2. So I have told you that length of gamma T1 T2 is really some constant time T2 minus T1. Now this is here I am assuming that T2 is greater than T1, but if you are not really assuming that, so you can put a mod here, C into T2 minus T1. Okay, so change in the length of this gamma T1 T2 is just some constant multiple of T2 minus T1. Okay. So that means if the parameter interval is finite, so then length of that geodesic is really finite. if it is infinite, then length of that geodesic is really infinite. Okay, so now let us second thing. So let gamma okay, gamma AB to N is a really be a geodesic. So then gamma, actually I have told you that the results, then gamma realizes the distance locally. Okay, so what does this I have to explain. What does that mean? I have really I have to explain this. So if T naught belongs to AB, then there exists some epsilon T naught, okay, so that if T1 and T2, this belongs to say T naught, okay, epsilon T naught minus T naught and T naught plus epsilon T naught. So then this length of this curve gamma T1 T2 is equal to distance between gamma T1 and gamma T2. So that means if you take T1 and T naught here, okay, T naught here, and if there is exist an interval around this thing, that if T1 and T2 will be here, then length of gamma T1 to T2 is equal to distance between gamma T1 and gamma T2. This is the Riemannian distance D. Converse is also true. So if gamma tilde is any piecewise smooth curve which realizes distance locally, and that is the meaning I have explained. Then gamma tilde is a geodesic. So this is a very, and geodesics are locally length minimizing or locally distance minimizing. These are the characterization of geodesic. Okay. Now you take an isometry. Okay. If you take an isometry, then the isometry really preserves the distances. Okay, that means actually if isometry will preserve distance, then using this property characterization of this geodesic, then you can, it is easy to see that isometry actually takes geodesic to geodesic. So, okay, so let us write that since isometries preserves distance. Now using this so-called property 2 mentioned above, okay, property 2 of geodesic mentioned above or mentioned in previous book. We see that isometries takes geodesic to geodesic. Takes geodesic to geodesic. Okay, so this is the fact I will you will use most often. And now another little bit discussion. So in actually differential geometry, there is a notion of zero-dimensional actually smooth manifold, and zero-dimensional smooth manifold is really your discrete topological space. So zero-dimensional perhaps your smooth manifolds are really are really discrete topological spaces. Okay, so similarly, we can talk about zero-dimensional Lie group and discrete topological groups are really zero-dimensional Lie group, and so you cannot really, if you have studied Lie theory, you cannot really avoid this zero-dimensional Lie groups, and so if you since there are infinitely many discrete topological groups which are non-isomorphic, so this has some importance in Lie theory. Now consider this Riemannian manifold. By Riemannian manifold, we mean we have always assumed this M is connected. Okay. So what is the reason we have really assumed that M is connected? Suppose M1 and M2 are two disconnected components. If you take P and Q here, and we want to define distance between P and Q, so for that reason, there should be exist some path joining this P and Q, and this cannot be possible when M is disconnected. So to define distance, it is necessary that in Riemannian manifold, so in such thing, we are really assuming that M is connected. Okay, so so Riemannian manifolds are so are connected. Okay, so in the definition of Riemannian manifold, we have assumed that we have assumed it is connected. Okay. Okay. Connected. So now the thing is, so suppose you really talk about zero-dimensional Riemannian manifold. So then that will be a singleton. Okay. So zero-dimensional Riemannian manifold is always a singleton. Is always singleton. So that for that reason, and this singleton, and this is not interesting for the point of view of geometry. It doesn't have any geometrical importance. For that reason, actually, we will talk about Riemannian manifold, which has a really dimension of m greater than equal to 1, or rich symmetric space also. We will really take this Riemannian manifold has dimension greater than equal to 1. Okay, so let us start a new topic, Riemannian symmetric space. So I will use this acronym RSS, or Riemannian symmetric space, and this term is purely coined by Dr. Pritam Ganguly, and I will really use this term RSS throughout my lecture in honor of Dr. Pritam Ganguly. And I hope you will not have any problem with it.
Thank you, Munada.
Okay. Okay. I think, is there anybody in the audience who has problem with this RSS? Okay.
Mona, even someone has problem, he or she will not say in the current scenario. Okay, please carry on.
Okay. So definition. Let MBA Riemannian manifold with dimension of M is greater than equal to 1. I am just mentioning it, but I told you. So M is called a Riemannian symmetric space. Or simply symmetric space. Symmetric space if for each P belongs to M, there exists an isometry SP from M to M, so that first thing is SP of P is equal to P, and second thing is DSP of P is really minus of identity. So this is my definition of symmetric space. Just look at this. Okay, so let M be a Riemannian manifold with dimension of M greater than or equal to 1. M is called a Riemannian symmetric space or simply symmetric space. For each field P belongs to M, there exists an isometry SP from A to M, so that SPP is equal to DSP and DSPP is equal to minus of identity. Now look at the definition. So SP is an isometry. It specifies a point and it specifies where also its derivative at the point P. So remark. So that means SP is unique by this rigidity term. So SP in the previous definition is uniquely determined by the rigidity of isometry. So that says basically given any Riemannian manifold, there is a unique way it can be made as a symmetric space. Okay, because isometries are really fixed by the rigidity of isometry. So first proposition I want to.
No, what did you just say?
So I say that this SP has to be fixed, right? Because SPP
Yes.
is equal to P, DSPP is equal to P. If the Riemannian manifold M is fixed, then in only one way, unique way, it can be made symmetric space. Because, okay, is it clear?
What do you mean by one way?
Okay, so I will clarify it later then. Okay, so you just assume that isometry SP has to be unique.
Yeah, that is fine.
See, the thing is, the isometric group is fixed, right?
Mm.
So suppose M is a Riemannian manifold. I want to make it symmetric space. So I suppose in two different ways, and one side I define something SP, and another way this I have to define this SP prime, say. Now, but both has to satisfy this condition. SPP is equal to P, SPP prime P is equal to P, and DSPP is equal to minus identity, and DSP prime is equal to minus identity, right?
So that part is clear that it has to be unique. This SP has to be unique.
That's what I am saying. Okay, so this is just don't worry about that thing. Okay, first. Okay, so first proposition I want to prove that this is an important proposition. So let M be an RSS, okay, Riemannian symmetric space. Then M is complete. So proof. Okay, so by Hoppe-Lino theorem, suffices to show it for that M is geodesically complete, because completeness is really equivalent to saying that M is geodesically complete. Okay? So I will prove by maximal geodesic in M. with domain of gamma tilde is really not equal to minus infinity to infinity. Okay, so I am really proving this by contradiction. Now domain of gamma tilde is really minus infinity to infinity. Then really domain of gamma tilde is really something like, it may happen in the three cases, like a to infinity, so minus infinity to a, or ab, where a, b are finite. So in this case, a cannot be really infinite. In the first case, a cannot be minus infinity. A cannot be plus infinity. And in this case, a and b are finite. So these three cases can be possible. So what I do, I will just reparameter this car little bit. Okay, so I will explain why I do want this. I want to reparameterize this by affine reparameterization. Parameterization. Parameterization. We can get a maximal geodesic. So this is the same geodesic, but I am repairing minus AB to M with 0 less than A less than B. Okay, so what I'm saying is, let us understand this diagram. So here is my, say, gamma tilde. Okay. So you
First,
take
you are taking the geodesic. So gamma is the geodesic from A. This domain is A comma B, right?
domain is minus a comma b. Okay, I will say that. Okay, so first you understand that why I am taking for this parameter. So you take this, suppose gamma tilde, this is a maximal geodesic. Okay, the first started with this gamma tilde. Okay, this initial, which has domain not equal to this minus infinity to infinity. This, so this domain is really, this domain is not equal to r. Okay, you take any point p. Okay, so that will divide this geodesic in two parts. Okay, so this is the, suppose this left segment, and there is something called right segment. Okay. So this is my left thing and right thing. So since this domain of gamma tilde is not r, it is possible to choose some p, so that this length of the left segment is not equal to the length of the right segment. So what I'm saying, you take any arbitrary point P, it will divide something gamma 2 in the geodesic into two parts, say gamma 1 and gamma 2. Gamma 2 will start from P and gamma 1 will end at P. So since domain of gamma tilde is really not equal to R, so it is possible to choose P, so that length of gamma 1 is not equal to length of gamma 2. So I am choosing my parameterization in such a way that this gamma 0 is really actually my P. Okay. And that is what I am doing. So here, see, by affine parameterization, we can get a maximal geodesic gamma minus A to B to M with 0 less than A less than B. That means length of this gamma 1, okay, because I am choosing this 0 less than A less than B, is really less than this length of gamma 2. That's all what I'm doing. So is it clear, Riju?
Not much. Can you explain me again? So the last you said mainly this
Yes.
how you choose this is has that this length of this comma less than equal this less than
So
equal to
this
comma.
is really say A infinitive. Okay. Domain is A infinitive. Okay. Suppose the domain is A infinitive, right? So arc length is really proportional to this change in parameter, right?
Yes, yes.
Yes. Yeah. So if you take any point P here, okay. So this is the length of this thing gamma 1. gamma. So here any point P will work. So what will be the length of gamma 2? Reju, what will be length of gamma 2?
So gamma 2 will be infinity. Means-
Infinitive. And length
Yeah.
of gamma will be some finite thing.
Yeah. Hmm.
Okay. So here this is the thing. Suppose, okay, so suppose this is something minus infinity to say say a. Okay. So real in this direction this will be infinity. So my p will be here. Okay. So if my p will be here, okay. So length of the right segment will be bigger, right?
Yeah. Okay.
Now,
Mhm.
okay, if you change this, so you take this gamma t was whatever gamma tilde t, you just define gamma t is equal to gamma of minus t. Then this parameter will be something like minus a to infinity.
Yes.
Okay, so minus infinity to infinity, and this will be like this, and then you can really replace that.
Okay. Fine.
It is not very difficult. So a and b is there. You take this something, and see a and b are finite. So you take, suppose this is the midpoint m. Okay, you take any something like p. Okay, any t where t is really less than m, and p is my gamma t. And length of this left side segment will be greater than sorry, less than the length of the right side segment. Is it clear,
Okay.
or I will tell you need
No, it
any
is clear.
clarification?
Yeah, it is clear.
So Annoy, is it clear?
Yeah, it's clear.
Okay, so this is what I am doing. Actually, you cannot really even without looking at the picture, you can do that. But I was want to just explain this thing. Okay. So for that reason, I have really taken minus a 0, minus a b. Means 0 will be lie inside this interval. So let gamma 0 is equal to real p. So this is my picture. Okay. So this is my p, and I have assumed that length of the b is greater than a. So I have this right side of the curve has greater length than this left side. Okay? That is the thing I am doing. So let gamma t is really gamma 1 t is really sp of gamma t, and t in between is really minus a to b. Okay. So now I told you that isometries take geodesic to geodesic. So this implies gamma 1 t. Okay. Since actually I am writing this first time. Since isometries take geodesic to geodesic, this implies gamma 1 t is also a geodesic. 1 t is also a geodesic. But this is gamma t is a maximal geodesic. Okay. So this implies gamma 1 t will be a maximal geodesic. Okay. So gamma 1 t will be maximal geodesic. Now what is gamma G10? Gamma 10 is sp of gamma 0. This sp of and gamma 0 is p. This is p. So and gamma 1 times prime 0 is equal to dsp p gamma prime 0. DSPP is equal to minus identity, and this is gamma prime 0. So this is minus of gamma prime 0. So gamma 1 2 is a maximal geodesic with this initial condition. Now let gamma 2 t is equal to gamma of minus t. So if you change, and gamma was a geodesic, and what will be domain here? See, minus 2 will be minus t will be really lie in between minus a to b, So here actually T should be like in between minus B to A. Okay, this is the domain of gamma 2. Okay. So now if you change the parameter affine, then that is also a geodesic. So this gamma 2T is also a maximal geodesic because gamma is a maximal. Okay, so now what is gamma 20? This is actually gamma of 0, this is P, and gamma 2 prime 0, you use that chain rule, so minus of, this will be minus of 2 gamma prime 0. Now look at this condition. Both gamma 1 and gamma 2 are the geodesic, has the same initial condition at the point 0. So that means gamma 1 T is equal to gamma 2 T. This implies gamma 1 T is equal to gamma 2 T for okay, T belongs to domain of gamma 1 intersection domain of gamma 2. So this is we have seen that. So let us draw the picture. So this will implies what? SP of gamma T is equal to gamma of minus T for some T belongs to this thing. Now if you really draw the picture, what is my SP of, this is my gamma. Okay, so what will be my SP of gamma? SP of gamma is something like this. Okay, so if you really move away from 0 in the positive direction, you will walk like this because okay, so this because this has a greater length. So if you walk positive, and what is gamma of minus T? If you go away from 0 in the positive.
Muna, why SP of gamma should be like this? It should be just the changing direction, right?
Yeah, that's what I am explaining actually.
Okay.
This will be changing direction actually. So I am explaining that gamma of minus T will really in this direction. So gamma of minus T, if you, but since this is the condition, SP of gamma T is equal to gamma of minus T, so this will fall on this line. Okay, so this picture will be like this. Yes, so this picture will be SP of gamma. So SP of gamma will fall in this direction, but but you will have an extension of gamma because in this side it was a greater length, so there will be an extension of this gamma, and that will be a contradiction. So what I'm saying that if you take SP of gamma, then you will just, it will flip this side to this side, and if the length is asymmetric, then there will be some extension. So, and that is the contradiction. Okay, and that is the reason actually I has chosen such P so that I will get an extension. Okay, so let us write the proof correctly. Okay, so it will be more clear little bit later. So so this is, so gamma 1, but as gamma 1 and gamma 2 are maximal, so domain of gamma 1 is equal to domain of gamma 2 because of maximality. Okay, and there is some point in the intersection, and that will be some minus A to B is equal to minus B to A. So this will implies A is equal to B, and but this is, which is a contradiction. A less than B. Is there anybody who couldn't understand this thing? Okay. Jaideep, is it clear?
Yes, ma'am.
It's clear. So let us write the theorem. So see, the thing is M is geodesically complete, therefore M is, hence M is complete. Okay, so this Okay, so that means in a Riemannian symmetric space, actually we don't have to worry about the domain. We don't have to be careful about the domain because domain is whole R for a maximal geodesy. Let them be a RSS. So yeah, it has two parts. Okay, so let this is thing. Let gamma be a maximal geodesic in M and okay, so let L belongs to R be fixed. So then I take the isometry, I take S of gamma L and I applied on this curve gamma T. This is real gamma 2L minus T. Okay, so if I put, so in particular, if I put L is equal to 0, so S of gamma 0, gamma T is equal to what? Gamma of minus T. Okay, so this is the first thing. So now the second thing really, B is really IM, isometry of IM, acts transitively on M. Okay. So proof is very simple, proof of ASA. So I take this thing, let gamma 1 T, this is really S of gamma L and gamma T. So this will be, so S of gamma L is fixed. So S of gamma L in isometry and gamma T is the your geodesic. Okay. So that means gamma 1 T is a maximal geodesic. So is a maximal geodesic. Similarly, if you take gamma 2 T, so gamma 2 T is gamma of 2L minus T, and I am changing the parameterization by afffinely. So gamma 2 T is also a maximal geodesic. So now this is really, now I will evaluate everything at the point L, gamma 1 of L. This is S of gamma L and gamma L. This is really is called gamma L. And gamma 1 prime L. So this will be ds. Actually, I will use the chain rule. ds of gamma L, and this is really gamma prime L. Now ds of L, gamma L, by definition, this is minus identity. So this is minus identity into gamma prime L. So this is really minus of gamma prime L. And so what will be gamma 2L? So gamma 2L is equal to gamma, if I will put LT is equal to L, so this will be gamma 2L minus L and this is gamma L. And gamma 2 prime L, so I will apply that the composition T going to 2L minus gamma 2L minus T and derivative that. This will be minus of gamma prime. So these are two maximal geodesics and which has same initial condition at L, at the point L, same value and derivative at the point L. So that implies gamma 1 T is equal to gamma 2 T. Okay, so this is really S of S of gamma L and gamma T is equal to gamma 2L minus T. Okay, so if I put L is equal to 0, putting L is equal to 0, we get, so S of gamma 0 gamma T, S of gamma 0 gamma T is equal to gamma of minus T. Okay, so I want to draw a remark. So let gamma 0 is equal to P. So this is my, so geodesy, this is my P and P is my gamma 0. So what it does is just, so if you go in the direction here, And if since S of P of SP of gamma T is equal to gamma of minus T, it just flips the geodesic around that P. If you are going in this direction, after applying SP, it will go in this direction. It just flips the geodesic. It takes this part to this part and this part to that part. Just flips the geodesic around the point P. Okay, since SP flips the geodesic around P about P, so SP is called geodesic inversion or geodesic flip, geodesic inversion or geodesic flip or geodesic symmetry. So this is the thing. Now this is the first first part of the theorem I have proved. Now I have to prove that well, IM acts transitively on M. So IM has a group action on M, which I have not defined. IM acts on M, and this is the action G dot P is really GP. Since G is a mapping from M to M, so G dot P is equal to GP. So check that this is a group action. This defines a group action. You can check that. So now B. So let us use a first case. Let B is the thing. So what I am doing, okay. So you know that Riemannian symmetric space is always a complete manifold. So I have told you a theorem somewhere that if any M is a complete Riemannian manifold, then any 2 point P and Q can be joined by a geodesic. Okay? If you after Hopf-Rino theorem, I have really stated this theorem. So let PQ belongs to M. So then as M is complete. So because I have proved that Riemannian symmetric space is complete, so there exists a geodesic gamma from AB to M with gamma A is really P and gamma B is equal to Q. Okay, so this is the thing. Now this is my picture, say P, and this is my Q, say. So what I do, I will take the midpoint M. Okay, so of this thing. Now I will apply this isometry SM to P. So if I'll apply SM, so since M just flips the geodesic around this M, and M is the midpoint, it will take actually P to Q and Q to P. Okay. So since really, so let us prove that. So this is clear from the geometry. Actually, I have. So let us just for the gamma of A plus B by 2 is equal to M. So SM of P. So this is S of gamma A plus B by 2 to P is what? Gamma of A, and I apply this A. So this is gamma of 2. This is my L. Okay, you apply this L 2 into A plus B by 2 minus A. So this is really gamma of P. This is really Q. This is I am using here A. I am using this A. So SMP is equal to Q. So that this implies I am acts transitively on M. Okay. So now this is what I did. Now a little bit discussion.
So this basically says that only the isometry of geodesic inversion they act transitively, right?
Yeah. Only
Means
that.
you may not need the whole isometry group.
Yeah. And we will prove that connected component of isometric group will also act transitively. So this is really will prove more actually. Connected component of this IM this. So okay, so this is the thing. So what I'm saying, okay, so let M be a Riemannian symmetric space. So M is complete. So now, so okay, let this. So this you take this gamma PB. Let gamma be the unique maximal geodesic with gamma PB0 is equal to really P and gamma PB prime 0 is equal to P. So since M is complete, so since M is complete, since so 1 will belongs to domain of gamma PB because whole R is the domain. So this implies exponential of P of B, this is called gamma PB1, this will be well defined. Is well defined because so earlier we are able to define exponential of PB where B is sufficiently close to 0, but here we are able to define where B is really any vector, right? Any vector in TPM. Now we have also seen that really this gamma PBS really exponential of P SB for all sufficiently small s. But here this and but what is the reason for we are taking sufficiently small s? Because exponential of PSB will make sense for only when B is very small. But now we are in this situation, this exponential of PSB will make sense for all S belongs to R. So then check that in this case actually gamma PBS really is equal to exponential of PSB or all S belongs to R. So you can take this as an exercise. You have to really do the run the same proof yeah, without any restriction of S because and another thing is see in a complete Riemannian manifold. So I told you that any two point can be joined by geodesic. So let Q belongs to M. So then then Q is joined. Q can be joined to P. Joined to P by an geodesic. This really emanating from P. So that means this implies P is equal to really Q is equal to exponential of P SB is really for some and this for some S belongs to R and B belongs to TPM because geodesics are of this form this exponential of P SB which starts from P. So Q will do this thing. This implies exponential of P is TPM to M is on 2. So this is actually a fact for complete Riemannian manifold, but since symmetric spaces are complete, so we are getting this thing. So this is an important thing, and we will really use those things later. So and another discussion. So this is a very important thing. Listen this to this thing very carefully. Let M be a Riemannian symmetric space. Okay. for P belongs to M, this SP is an isometry. Okay, so you take this SP square composition. This is SP composition SP, and this belongs to IM. Composition of two isometries is an isometry. So SP square is P is really SP composition SP of P. This is P. Okay. Now what is DSP square? Okay, DSP square at the point P. So DSP square at the point P. This is DSP P. DSP P. I am using this rule that D of F composition GP is equal to DF GP composition DGP. So that means this is minus identity and this is minus identity and this is identity. Look at the SP square is an isometry. It fixes this point P and DSP square P is equal to identity. Now by rigidity of isometries, I will take 5 more minutes or 10 more minutes probably. So just we will finish this, okay? By rigidity of isometries, this SP square is equal to really identity. Now as dimension of M is greater than or equal to 1 and this DSP P is minus identity, so SP cannot be identity. Okay, this is the part. That's where I am using this. So SP is not identity. So that means that these such maps are called involution, which are not identity, and its square is a. So this implies SP is an involutive isometry with which fixes P. So what is the definition of involution? Involution, the definition is something. So I think you should aim up G from say X to X is an involution. If G is not equal to identity and G square is equal to identity. So this is so SP has an involutive isometry, so it fixes this P. Okay, so now you take any normal, let UP be any normal, be a normal neighborhood of P in M. Okay, so I take this so-called UP. This is my picture, and this is my point P. And I have told you that any 2 point in this neighborhood are joined to a unit geodesy. Okay, so and the geodesics will not meet in this neighborhood also. So this is my suppose something like this is actually made up of only geodesy. Now if you will apply this SP to this, and SP actually what it does, it just flips the geodesy. So it will just flips the geodesy about the point P. So it is clear that in this neighborhood, the only fixed point of SP is P. So only it will flip the geodesic. So the only fixed point of SP is in UP is P. So since okay, SP flips the geodesic. Sorry, about P. The only fixed point of SP in UP is equal to P. This implies P is an isolated fixed point of an involutive isometry SP. Okay, so conclusion. So let M be a Riemannian symmetric space. Then each P belongs to M is a fixed point of an involutive isometry SP of M. Is an isolated fixed point. Is an isolated. This is isolated is really important. Okay.
What do you mean by isolated here?
Sir, in UP, only P is the fixed point. Okay.
In that UP normal
Neighborhood. So that means in that neighborhood, actually, all P is the only fixed point. So that means each P belongs to M is an isolated fixed point. Let me explain that.
right.
So that means they are. That means this precisely means this means there will exist a neighborhood B of P in M such that if SP V is equal to V or some V or some V belongs to B, then this implies V has to be V. Is it clear, sir?
Yeah. Nice.
Okay, so this is the thing. Now our converse is also true. So let us do this thing actually. So conversely, suppose M is a Riemannian manifold. So that each P belongs to M is an isolated fixed point of an involutive isometry SP of M. Okay. So conversely, suppose M is a Riemannian manifold, and I am assuming that each point P belongs to M is an isolated fixed point on involutive isometry SP of M. So that means we have already this information SPP is equal to P. We have to only show that this thing DSP P is equal to minus identity. Okay, so to show that let A is equal to say DSP P.
So
So
what do you want to show here?
What do you want to show?
M is a Riemannian symmetric space.
Right.
So for that I have an isometry SP, which is fixing this P. This is really there. Actually, I think I should do. I will do it this tomorrow. Actually, I need 5 minutes more, or will I continue? Just finish this. Pritam,
Yes.
will I finish this?
I have no problem if you continue.
Okay, so just finish this thing then. So this SPP is real P. Okay, and DSPP. Okay, I have to show that this is minus identity. Then that will be imply that M is a symmetric space. Okay. So to show that, okay, so to show that, let A is equal to DSPP. So this SP square is equal to really identity by this by assumption, because SP is an involution. So that means D of SP P composition D of SPP is equal to really identity map. So this implies A square is equal to identity. Now this implies eigenvalues are of A are plus minus 1. So let B plus is equal to B belongs to B, so that AB is equal to B. So B minus is equal to B belongs to B, so that B belongs to TPM, not B, sorry. B belongs to TPM. So that AB belongs to B, and this B belongs to TPM, so that AB is equal to minus B. This is really plus 1 eigenspace, and this is minus 1 eigenspace. And TPM will be really B plus B minus, direct sum. Now if B belongs to TPM, then you can write, okay. So what I have to show? I have to show that A is minus identity, because A is the DSPP. So that means I have to show that B plus is 0. Okay. So M is to show that B plus is 0. So let us see. So let gamma from some small interval minus epsilon to epsilon 1 be a geodesic in M with your gamma 0 is equal to really P, and gamma prime 0 is equal to V. Okay. So M, we do not know this. This will exist in a neighborhood of 0 only. This geodesic. Now let gamma 1t really your SP of gamma t. Then this will be also a geodesy, because SP in isometry. So T will be n minus 1 to epsilon. Now what is gamma 1 0? Gamma 1 0 is really SP of gamma 0, and SP of P, this is VP. Now what is gamma 1 prime 0? So DSPP, this is gamma prime 0, and DSPP is your A, and gamma prime 0 is B, but B belongs to B plus, so this is B. So as B belongs to B plus. So that means this gamma 1 and gamma has really same initial condition at the point 0. So this implies gamma 1t is equal to really gamma t for t belong to, and this domain is really minus 1 to minus epsilon to epsilon. So what is gamma 1t? This is really SP of gamma t. This is really gamma t for t less than minus epsilon 1 to epsilon 1. Now I have not used that P is the only isolated fixed point of SP. So let B be a neighborhood of P in M, so that only fixed point of P in V, fixed point of SP of SP in V is P. Okay. So I can choose my, so let 0 epsilon, yes, be sufficiently small, so that this gamma t belongs to B whenever t in between minus epsilon to epsilon. I can choose that. So earlier this was my epsilon to epsilon 1 SP of gamma t is equal to gamma t for t in between minus epsilon to epsilon 1. Let B be any neighborhood of P in N, so that only fixed point of SP in B is P. I choose my epsilon sufficiently small, so that gamma t less than B whenever epsilon minus T lies in between minus epsilon to epsilon. Now since epsilon is smaller than epsilon, so SP of gamma t is equal to gamma t for this thing, but as gamma t belongs to V, and V SP has only fixed point in V is P, and SP has only fixed point as P in V. So this implies gamma T is equal to P for all T in between minus epsilon to epsilon. So that means gamma prime 0 is equal to 0, and this gamma prime 0 is equal to V is equal to 0. So this implies our V plus is equal to 0. So this implies DSP P is equal to A is equal to minus identity. So this implies, so this I have done for, since P is arbitrary. So this implies M is a RSS since P is arbitrary. Okay, so let us write the proposition, then we will stop theorem or proposition. So let M be a Riemannian manifold. Okay, so then the following are equivalent. So M is a Riemannian symmetric space. So and for each P belongs to M, there exists an involutive. For each P belongs to M. Okay, so each P belongs to M is an isolated fixed point of an involutive isometry SP of M. So and here this if you start with the second definition, for existence of involution, you need at least M has to be contain more than 1 point, and therefore M cannot be singleton. So dimension of M will be greater than or always equal to 1. So this is my
So Muna,
proposition.
I have a slight doubt. So in the second statement,
So,
this SP depends on P, right?
yes.
So given any P, there should exist an involutive isometry so that P is an isolated singular point for that isometry.
I have written that each P belongs to M is an isolated fixed point of an involutive isometry SP.
So are there some cases where this condition is easy to see?
Okay, we will give a lot of example of symmetric space. So those are, any symmetric space is an example for that. Okay, we will see that. Yeah, so see once you symmetric space is really, you prove something is symmetric space, and you know that okay, in this thing it is a, in the normal neighborhood it is a geodesic inversion SP, and so if you, so in that normal neighborhood P is the only fixed point. So as soon as I will give you some example of symmetric space, you will see this thing very clearly. So but examples I will do it tomorrow, and I will have to prove one more proposition, then we will go to example, take up example.
No, my question was these two are equivalent conditions, either a symmetric space or it has isolated singular points, right? So what I'm asking is, are there some cases where the second condition is easy to see?
Oh, I don't, actually I do not know. You will say that we will use this second condition, but mostly actually we will work with the first criterion. Okay, what second thing is will be useful, but I do not know that.
Okay, fine. Thank you.
Is there any question, or I'll just stop you? I have exceeded time.
If IM is connected, will SP be unique?
IM is connected. See, the uniqueness is first from the rigidity of isometry.
Yeah, right. I see. Okay. Yeah.
Because SPP is equal to P and DSPP is minus identity.
Right.
So SP has to be unique actually.
Okay.
So is there any question or?